k then, right? What is the coefficient k here? What could it be? Well, k here can be determined through the fact that the wavelength is known, right? If the wavelength lambda is known, the distance between the two peaks is known, then we can use that to determine k, right? Because k should tell us basically how the distance is converted into the phase difference, right? Or in other words, if we look at the wave, we see that the distance lambda between the two red peaks, right? Between this peak and this peak, this distance should be, it is lambda, and it should be corresponding to a phase difference of 2 pi, meaning that the sine function comes back full length, full circle, right? So we just complete a period. And so in that case, we need, if we increase x by lambda here, right? If we increase x by lambda, the argument inside the sine function would change by lambda times k, right? So, and we need that change to be equal to 2 pi. That means we have the condition that k lambda is 2 pi, which solves to the fact that k is 2 pi over lambda. And so, if we know the wavelength lambda, we can determine this coefficient k, the wave function, which is just 2 pi over lambda. And this k, it has a physical meaning to be the angular phase difference corresponding to a unit length of translation in the x direction. So if we look at the wave, if we start off at some position x0 and we travel a distance x, then the phase difference would be just k times x, right? So if we travel the distance of lambda, which is the wavelength, then the phase difference should be one cycle of the sine function, which is 2 pi. Now, if the parameter k here is usually called wave number, right? And it is usually in the unit of radian per meters, meaning that how many phase difference in radians do you acquire by traveling 1 meter within the wave at fixed time, which is a bit challenging, but let's say if we could achieve that. Then now with the wave number defined, we can talk about the last parameter, which is the propagation speed v, right? We looked at it earlier, right? The propagation speed v appearing here, so that we fix how the wave pattern travels over time, right? How it changes position over time. Well, this propagation speed v, it must correspond to the wavelength lambda and the period t, capital T, such that if we consider the wave propagating, the wave needs to look the same after the time capital T has passed, because it is a period of the wave. So if we start at some position x, right, and we travel for one period of time, for the time capital T, we need to have been moving for the distance of a wavelength lambda. In other words, the propagation speed has to be the ratio lambda over t, right? It's how far we move delta x divided by how long the time has elapsed in delta t. And now we know that the reciprocal of t is the frequency f. So this gives us the famous relation that the propagation speed of a wave is the wavelength multiplied by the frequency. And sure enough, if we take lambda to be in meters, right, which is the standard unit, and the frequency to be in hertz, which is 1/second, right, then lambda f would give us the speed in meter per second. So that's just the unit consistency here. Okay, so with this propagation speed, right, we know that v is lambda times f, or lambda divided by t. We can put v back into the wave function, right? And if we look at the wave function, we put lambda times f here, right? And this is 2 pi over lambda, where the coefficient of t is just 2 pi times f. And sure enough, the coefficient of t, which is kb, is just 2 pi times f. And this is usually defined as another Greek letter, omega. And this is what we call the angular frequency, which measures, if we stay at a fixed position, it measures how much phase difference elapses over the time t, right? So per unit of time, how much phase has changed. So if we let the time of a period elapse, then the phase should change by 2 pi, and sure enough, that is the case. And then with all these parameters, we would be able to relate V to omega divided by k, but that's some secondary relation, right? Because again, omega is 2 pi f, k is 2 pi over lambda. This, we plug in the angular frequency and the wave number expression, then we just get f times lambda as b. So that's kind of secondary. Now, with all the pieces together, we can write down the wave function as just kx minus, as just a, the amplitude, times the sine of kx minus omega t plus some initial phase phi, right? So this is usually how we would write it. It's kind of a general expression. And from this function, we know that we can determine the wavelength from k, the frequency from omega, and the amplitude in initial phase directly, right? And now, with all these considerations for a sinusoidal wave traveling in a positive x direction, we can also do the same exercise for the wave propagating in the negative x direction or toward the left, and we get this wave function y minus. Essentially, as promised, we just flip the coordinate x and replace x anywhere by negative x, and that should give us the result. And everything else remains the same. K is 2 pi over lambda, omega is 2 pi f, and those are just positive numbers. So you just have an extra minus sign right here. So no big deal, right? Just flip the definition of x. Because if you are traveling with a speed of like 100 kilometers per hour, if you're traveling north and you say north is positive, then if you travel south, then your speed is plus 100. But if you flip the coordinates such that south is positive, then your velocity will become negative of 100. And that is just like, you just want to keep things positive. You just want to keep k and omega and everything positive by flipping the coordinate x right here. And that's it. Okay, so with all these introductions, right, we can try to play with some wave, right? So if we have, so this is quite a direct exercise. So we have like a wave, a traveling wave like we have just been looking at, right? So that means it would have a wave function like this, right, or this. And because it is traveling in the positive x direction, we actually have this function right here. Now, with that wave function, we consider a wave with amplitude of 15 centimeters, wavelength of 40, and frequency of 8 hertz. So some of them is labeled here, right? The amplitude is 15, and the wavelength is 40, the distance between the two peaks. Then, and besides those information, we also know that at t equals 0, the displacement at the origin x equals 0 is also 15, so it is as drawn here, right? So we happen to have the peak exactly at x equals 0 when the time is 0. Now, for part A, we just want to find the wave number k, the period t, the angular frequency omega, and the propagation speed v of the wave. And so this should be quite straightforward. And then for part B, we just want to find the initial phase and then write down the wave function. So maybe why don't we take like 5 or 10 minutes to work out this one and then see what we get. So these are the answers, so you can just cross-check with what you get. I can write down some equations in one of the boards if that's helpful. Yeah, that one would do. You want to see how long my arm is? Oh, it's actually not that bad. Actually not that bad. Yes. I think that's all you need here. Yeah. That's all you need. The rest is math.
Okay.
Yeah, and talking about formulas, the formula sheet for the midterm should be up like today or tomorrow. The formula sheet that you can like it will be given to you in the midterm.
Oh.
Okay. It's not supposed to be scary. It's supposed to be fun. Oh yes, I forgot to upload the slide. I should have. My bad. I'll do so right after the class.
What's this again? What's this again?
Oh right.
What is
The T is just a reciprocal of F, right? Usually, period and a frequency.
how to get this? Frequency, what? 15 centimeters. What's wavelength again?